My dudes, how are you? So, fluids. This is we're flashing back a little bit um, to when we talked about. Well, we talked about buoyant force, a force that a fluid um, can exert on an object that's submerged in it, and we use that as a case study for different kinds of forces. We're going to talk a little bit more about fluids as a topic. And what's nice is we'll be able to show you really why, where Archimedes' principle, that buoyant force idea, comes from. All right, so we need to be able to define a couple of characteristics of any fluid. One is its density. Now, before I even do this, I should say that fluids include liquids and gases. Gases are fluids. Fluid doesn't mean liquid. A fluid is something that can flow through, I don't know, flow through an area. Okay, so air can move from one place to another and demonstrates the same properties or similar properties that water does, but they're obviously different things. But we can refer to them both as fluids. Any fluid has a density, right? We just call that rho, defined to be ratio of mass per unit volume, right? Measured in kilograms per cubic meter for us. Any and every fluid exerts a pressure on the walls of a container that confine it. All right, and pressure is defined to be the ratio of force per unit area. All right, and that therefore is measured in newtons per square meter, which we call a Pascal. A Newton per square meter is a Pascal. Okay. Fluids also can occupy volumes. It's not necessarily a characteristic of the fluid. But yeah, those are two big ones we need to be familiar with. Notice this is a capital P for pressure, and we know that density uses our lowercase Greek rho. Okay, atmospheric pressure, these are just some givens. Atmospheric pressure that we call 1 atmosphere, that's equal to 10 to the 5th pascals. It's a number you'll be given, but wouldn't kill you to have at the back of your head, back of your mind. Yeah, something that fluids all do. Well, fluids exert forces, like we said, on the walls of any container that confine them, and those forces are always perpendicular to the surface upon which the force acts. All right, so if we think of a balloon, right, here's a balloon. Well, the air pushes out that way, and or whatever's in there, and out that way, and out that way, and out that way. So those forces are always perpendicular to any surface. Okay. Now, the fluids exert forces, right? And pressure is a measure of force per unit area. But pressure, good to know, is a scalar. Okay. Yeah. All right. So here's a simple pressure and force and area example. The question is, the air in this room, what force does it exert on the palm of your hand? Well, if you look at the palm of your hand, let's see, let me trace my hand. Oh boy, careful. Trace my, come on, blue pen. Trace my hand. Oh, my big mitten hand. Here's my palm. Really, I mean, if I'm looking at it right here, this is just about, I would call this a tenth of a meter. It's on the order of a tenth of a meter, and it's a square, okay? So if we want the force that air exerts on my palm, well, I'm going to use that pressure is force per unit area, and therefore force is pressure times area. Well, the pressure of the air is 10 to the 5th pascals, and the area is 0.1 meters squared, or, well, that gives me a force of 10 to the 3rd newtons. That's 1,000 newtons, or almost like the weight of 100 kilograms, but I sure don't feel it, right? That means the air is pushing on my hand that hard. Well, yeah, why don't we feel that? I guess, A, because we're sort of used to it, and B, because there's the same force in the back of my hand pushing the other way, so certainly that's the reason my hand doesn't accelerate one way or the other. And it just sort of shows you, I think, that if you were to just take me and put me in outer space and there wasn't air pushing on my hand or on all parts of my body, pushing inward on all parts of my body, you know what would happen to me? Well, it wouldn't be pretty, folks. In addition to being super, super cold up there, boy, oh boy, I think I'd just come flying apart in an instant. Not in an instant, it would take some time, but without that force of air holding us together, there'd be a big mess in a big hurry. Okay, so there's that. Here's another good one. This is a very powerful vacuum cleaner. It has a hose that has that diameter. What's the weight of the heaviest brick it can lift? Now, a couple of things here. Let's look at this vacuum hose, right? It comes down like this. And then here's our brick that's, sort of stuck on there like that. The question is, how do vacuums work? Well, it's pretty neat. Is if we say this is a, quote, very powerful, we're going to assume that it can create a condition in here where pressure is 0. Now, the old Dyson doesn't give you a complete vacuum, but this very, very powerful one, let's assume that it does. There should be 2 C's in here, right? I don't know. I can never remember. And so here's the deal. We always think, it's easy to think of vacuums as pulling dirt into them, right? Or in this case, pulling the brick upward. Well, really what happens is what we do is just plain old get rid of the fluid, the air, in that area. Really, in this area here. Well, there's still air that pushes up right there. Right, in this same area. So it's not so much that the vacuum pulls the brick up, it's that the vacuum gets rid of the air in there that would push the brick down. And if we get rid of that air, then all we're left with is the upward push of the air below the brick. Pretty neat, huh? So what we can say is, what's the weight? Well, if we look at the brick, we've got its weight, and then we've got this force that air exerts, which is equal to pressure times area, right? Which we'd write as P atmospheric times, this is a circular hose, pi r squared. Don't forget that your R, 0.015 meters. 3 centimeter diameter is a 1.5 centimeter radius. We use that to find the area. Okay? So whatever that is, it is. All right, but neat thing about vacuums, right? They don't necessarily pull, they get rid of the push. I dig. Onward. So, what we call pressure at a depth. Well, let's look at this little subset of the whole liquid or fluid that's in there. All right, we're going to make an assumption that we call this fluid an incompressible fluid, which means its density is the same everywhere you go. That doesn't happen in air, right? The density of air near the surface of the Earth is much greater than it is it's greater than it is higher up. All right, So we look at this subsection of that fluid, right? And the big deal is that subsection of the fluid, it doesn't go anywhere. It just sits there. This is what we call a static fluid, right? A fluid where nothing's moving. If we look at this subsection of that fluid, well, there are actually forces acting on it. All right. First of all, the rest of the fluid pushes in like this, and in like that, and in like this, but from the back, in like that, and in like this, and from the back, in like that. And all these forces around the outside are all balanced by other forces on the other side, right? So there's a symmetry of all these forces in the kind of horizontal plane. Okay, so all those forces add up to nothing. All right, but there's also the fact, well, this water weighs something. And there's a force exerted on this area that we can call pressure above times area, right? Force is pressure times area. And there's a force below exerted on the same area. It has to look like this, and I'm drawing it to scale. Pressure below times area. And if we do a simple net force statement here, we say that pressure above times area plus mg is pressure below times area. Okay? It keeps that part of the water from moving anywhere. Now you'll remember this, pressure area. Notice, or remember, I'm going to write mass as rho v. Actually, hopefully you remember this. The weight of the water, the weight of the fluid, rho vg, remember that? Is pressure below times area. And now what I'm going to do is say that, well, if I do this, divide everything by area. Well, that goes with this goes with that. And the deal is that if we divide the volume of this thing by the area, well, the volume of it is the area times its height. It's a cylinder. This thing has a height that we'll call h. So this turns into pressure above plus rho g h. Here's the rho, here's the g, and h is v divided by a. Is pressure below. That is an expression for what we call pressure at a depth, or pressure at depth. The one big deal is that pressures lower, below, are always higher than pressures above because of the weight of the extra fluid above you. All right, so here's your new expression for what we call pressure at a depth, for a static fluid, a fluid that's not moving. Fair enough? Okay. Now, how do we measure pressure? A couple ways. One of them is to use something called a barometer, which you've heard of. And what you do with a barometer is you make a place here where pressure is 0. And then you make a place here where the pressure is, well, open to the air. And really what happens is air pushes down on this fluid wherever it can sort of access the fluid, and that pushes the fluid up here to a certain height that we'll call h. And so what you can say is, well, let's see, we could relate the pressure at this height to the pressure at this height. And we could say the pressure below, which is air pressure, is the pressure above, well, that's 0, plus rho g h. So depending on the density of the fluid that you use in your barometer, air pressure will make the column reach a certain height. Okay? One way to measure pressure. Here's another couple of ways. Well, sorry, another way. It's called the open tube manometer. All right, and so what you do, as they show you, is you open one end of a tube, and you hook the other end to a sample of something. And, well, in a case like this, when we open this valve here, well, the fluid is almost like, well, if the pressure in here is, notice what it says, less than an atmosphere. We have atmospheric pressure here. We have less than that over here. So the pressure below P atmospheric is the pressure above, which is the pressure here, plus rho G H. Or here is H. So notice, atmospheric pressure is greater than that pressure. The other way you do it is, in this case, notice the pressure in the sample is greater than an atmosphere. So that means that the pressure below, which I'll call P gas, how about that? P gas, that's the pressure below, is P atmospheric plus rho GH, where here is H. So here the pressure in the gas is greater than atmospheric pressure. Now you notice that what I'm doing is, maybe it looks like I'm behaving a little bit willy-nilly with heights, right? Because really what we like to do is look at part of the fluid maybe like this. And I'm just measuring the height from here to here. But we can use, this is called, not Archimedes, it's called Pascal's principle. Pascal's principle, is that Pascal's principle? No. Is it? I don't even know. But here's the big deal. I'll just say it like this. Same height and same fluid means same pressure. So, notice, I talked about the pressure here. Well, that's the same as the pressure here, because this is the same fluid, and pressure really depends only, like we said, pressure is pressure above plus rho GH. So all that matters is how deep you are into the fluid. And here, we're at the same depth that we are here. Okay? Okay. Now, a mercury barometer, blah, 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 vacuum at the top, measure the height. Now, normal atmospheric pressure, you've probably heard this. 760 millimeters of mercury. You ever heard that for atmospheric pressure? I have. Constantly. So we want to know what the density of mercury is. So what we're saying is that in a mercury barometer, what happens is you get a column of mercury that rises up 760 millimeters, or 76 centimeters, or 0.76 meters. So a mercury barometer, atmospheric pressure pushing down on this fluid pushes the, what do you call it, the mercury up 76 centimeters, or 0.76 meters. Now remember what we said about a barometer. We said that here pressure is 0. Here pressure is P atmospheric. So we can write an expression for our pressure at a depth P below is P above, P above, nothing. I'll just write 0 plus rho GH. So the density of mercury is going to be atmospheric pressure divided by GH. Density of mercury is going to be 10 to the 5th pascals divided by 10 meters per second squared times 0.76 meters. Now notice when I type or when I say 10 to the 5th on my calculator, I do 1 E5, 1 times 10 to the 5th, divided by parentheses. Well, I'll do, let's see, 7.6. Yeah, and you get a density of mercury of 1.3, let's call it, times 10 to the 4th kilograms per cubic meter. Dense stuff. Remember what the density of water is? Density of water, 1,000. This is 13,000. Dense stuff. Yeah, so I wanted to build, I thought, hey, why don't we build a barometer using water? Why not? It's infeasible. It's not a, it's infeasible means it's like not worth trying because there's something a little bit ridiculous about it. There's something a little bit, it would just be kind of a pain realistically to try to do. That's what infeasible means. Tell me why. And I would involve some algebra and some math and some physics. All right? Just calculate why this is infeasible. And with that, I bid you adieu. Okay? Goodbye.